Now, suppose we have, that we're talking about Lagrange multipliers, so maybe I'll just write those words up here where you can't read them. Lagrange multipliers. Written softly with a chunk of chalk, so it's small with a chunk of chalk, so it might be a little hard to read. But that's what we have, okay? Now, in your textbook, as in most textbooks, the textbook starts off with a big incomprehensible statement and then proves it. Okay? I'm going to start off with the geometry of the situation, and I'm going to build up that statement in such a way that you'll understand it. And then you can choose which way you want to work. Okay? In proving the statement, you do develop understanding of the statement, but sometimes that's daunting. So I'm going to approach it from the opposite end here. Okay, so you got some function f of x, y. Now we're familiar with functions of two variables, and we're familiar with the fact that if we have a path here, that the function could be evaluated at points on the path. Now I'm just saying, okay, let's say that we evaluate the function here, 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 and here, and the numbers we get are 1, 2, 3, 4, 5, and 4. Okay? Now if this is a nice curve and it's a nice function, you know, differentiable and all that stuff, and the curve is smooth, we expect that somewhere between 4, 5, and 4 we're going to hit a maximum value, at least a relative maximum value. And maybe we'll hit several maximum values in there, depends on how weird the function is. But at least between here and here we do expect to find a maximum, and we expect maybe it'll be kind of close to the point where we have the value 5. Now it could go from 4 up to 5.8 and then down to 5, so it could be decreasing when it gets here. Or it could go from 4 to 5 to 6.7 over here, in which case it would be increasing as we move along the path in this direction. We don't know, okay? It depends on the path. It depends on our function. But what we do know is that if at point A, which might be this point, okay, we have the situation I've depicted here, we can figure out whether this point is a maximum or a minimum according to this situation. So let me explain the situation. I'm saying that the normal to the curve is here, okay? And I'm saying that the gradient of f is here. If we have the parameters of the curve, or if the curve is a level curve of some function of two variables, we're going to be able to calculate a normal to that curve. And if our function f of x, y is differentiable, we will be able to get the gradient. Okay? So, if this is our situation, just as I've depicted it, could we possibly have a maximum or a minimum at this point? Relative maximum or minimum. So I'll just confine attention to relative max, but it could be relative min just as well. Okay, can a relative max of f of x, y along the curve occur at the point A as I've depicted the gradient and the normal? Well, I'm going to say it can, okay? And I'm going to show you why. Okay, well, the question then is, as we move along the curve, is f of x, y increasing, decreasing, or neither at this point? Now I've drawn the same situation down here. You know, things have rotated a little bit, but it's the same idea. We know what the normal is. We know what the gradient is. So, is the function increasing, decreasing, or neither at this point? If we're at a relative max, it had better not be increasing, because that means we go just a little further, we get a bigger value. It can't be decreasing, because that means if we go backwards a little bit, we get a bigger value, right? So the value is going to change, so we can't have a max at a point where, moving along the curve, our function is either increasing or decreasing. And same thing about a minimum. Okay? You can think through why that's true, but it's very similar. So, if we're at a relative max, the function can't be increasing or decreasing, and there's really no question mark involved with that. The function has to be not changing. It has to be neither increasing nor decreasing. Okay? Now, here's our situation again with this picture. The motion at point A is along the tangent line. Whether you're going this way or this way, the motion is along the tangent line at this instant. At this instant, you're moving in the direction of the tangent line. Okay? And the tangent line is perpendicular to your normal vector, isn't it? Okay, so we're moving in a direction perpendicular to our normal vector. Now I ask, what's the directional derivative in the direction of this tangent? Well, if we have a unit tangent vector either in this direction or this direction, so let's just put it in this direction, but it doesn't matter. Okay? So there's our unit tangent vector in the direction of motion. If we're moving this way, well, it's in this direction of motion. It wouldn't make any difference. Then the directional derivative in the direction of t is del f dot t. And we understand why that's so. Del f is the direction of maximum increase. And the magnitude of del f is the rate at which the value of f is increasing if we move in this direction. If this direction has a component, well, if the del f has a component in the direction of t, that means that the function is going to be changing in that direction. Okay? And the rate of change is just going to be del f dot t. Okay, so the directional derivative in the direction of our unit tangent vector, t, is del f dot t. Okay? And as I just said, if del f dot t isn't zero, that means that the function is, that our values are changing as we move in the direction t, which means they're changing as we move along the curve. So we can't have a relative max or min. So, in the picture, del f isn't perpendicular to t, so del f dot t isn't zero. It follows then that the directional derivative is non-zero, meaning the value of function in the direction of the curve is either increasing or decreasing. And it follows then, from what I said earlier, that the relative max or min can't occur at this point. Okay? So what's the condition under which a relative max or min could occur? Think about that, and we'll pick that up next.